Okay, I just wanted to mention what slope fields kind of look like in at least two special cases that we've covered in previous videos about first order equations. So here is the slope field associated with the equation y prime equals negative y. Now, what we know at this stage in our lives, I hope, is that this is what's called an autonomous equation. Y prime equals negative y. Um, this is a special case of the more of the equation which we've studied quite a bit in the past, y prime equals ky, where k here is negative 1. But what I want to focus on is the fact that it is autonomous gives a certain quality to the slope field. Okay, so I'm looking in the textbook here. Do you notice something about this slope field here? Do you notice in particular that this slope field is I'm going to say the technical word, it's horizontally invariant, meaning that as you look at horizontal lines in the plane here, do you see that all of these slopes of the line segments in this slope field are in fact equal? That's what I mean by horizontal invariant, right? As soon as you set a horizontal level, which is a y coordinate, then you know the slope field, or the slope of the slope field at every point along that horizontal line. So then this should mean, if we believe in this integral curve idea, this should mean that integral curves, we should be able to move integral curves horizontally and again get solutions. So I think that's something that we can check. I think that's something that we can detect. So let's go ahead and do that. Let's take, for example, y prime equals ky. So I can't draw the slope field here for you, but you can imagine it from the textbook. So we have y prime equals, oh, I'm sorry, and we have to be specific about k here. K here is negative 1. So y prime equals negative y. So based on stuff that we did in the previous videos, we know the general solution to this. The general solution to this is y equals c times e to the kx, right? K here is negative 1, so we get negative x, okay? Now, my claim is that we should be able to take a fixed solution to this and move it horizontally and again get a solution. And this is a manifestation of the fact that the slope field has that horizontal invariance that I was telling you about. This, like, you can move all of the, you can, it's hard to say, you can move all of the line segments horizontally, right? And nothing changes about the slope field. So you should be able to take a fixed solution to this differential equation and move that horizontally, and that should again be a solution. Now, is that the case? Well, if you're given a function, you know it has a graph. That graph is going to be a slope field. If we go back to the picture here, in this picture, these red curves are exactly of the form y equals e to the negative x for some, sorry, y equals c times e to the negative x for some choice of c. They're exponentially decaying curves, right? The graphs of these things look like, maybe I can draw it, look like this. For some choice of c, all right? It's not the greatest picture, but you can deal with that. And then what happens though if we take such a y equals c times e to the negative x and we horizontally translate it? Well, horizontal translation corresponds on the function level to replacing x by something like x plus some number, right? We know that we can horizontally translate a graph in particular to the right if we do that, by replacing x with x plus this distance, whatever this distance here is. If I call that distance, maybe I shouldn't call it k. Let me call it d, right? Like, let's say that we move this thing a distance of d horizontally everywhere. And you have to imagine, I'm not good at drawing, okay? So you have to imagine that this happens at every point along this curve. It's really not convincing over here. Oh no, what have I done? I don't know what I'm doing anymore. But hopefully you understand what I'm saying here. I've shifted this curve here by d units horizontally. On the level of equations and such, this red curve is going to be given by y equals c times e to the negative, and then we replace x by x minus d. Don't forget, if you want to translate d units this way, to d units to the right, then you replace x by x minus d. This is like pre-calculus stuff, okay? Well, the question is this really a solution? Because my assertion was that if I translate this curve horizontally, that I am going to get a solution. And indeed it is. Watch. This is just the same thing as c times e to the negative x plus d. Right? All I did is I distributed the negative sign. Then I can rewrite this as c times e to the negative x times e to the d. That's just by rules of exponents. And then I want you to observe that this here looks like a fetus, but that blue thing right there, that's just a constant, right? So I might as well just, in other words, this y in red, this thing in red right here, okay, is again of the form y equals ce times e to the negative x. So it's again a solution. So I was right. If I translate a solution to the graph, let me say it like this. If I translate an integral curve to this slope field for this autonomous equation horizontally, I again get a solution to this. I again get a solution to this differential equation. I again get an integral curve. Okay? All right. A simpler idea is what happens when your slope field, and maybe I'll just say this out loud because I don't have good pictures, right? It's always hard to get pictures. But maybe something to say is that, I'm just thinking for a second. Okay, here's what I want to say. Imagine that your differential equation was of the form y prime equals f of x, right? Not an autonomous equation, but something like this. Then we know, right, that the general solution is going to be y equals the integral of f of x dx. Okay? And in particular, if we know one antiderivative, then all we need to do to write down this integral is we find some antiderivative big F, and then we just tack on a plus C, right? Now, I want you to try to imagine the the slope field corresponding to y prime equals f of x. Notice that this does not depend on y. It doesn't depend on y. So as soon as we fix x, we know the slope of the line segments in the slope field for all of the points with that x coordinate. In other words, the slope field here is going to be vertically invariant. So I'm going to say vertically invariant slope field. Whereas with the autonomous equation, we had horizontally invariant slope fields. Okay, neat. Do we see that coming out in the general solutions? So what this should mean, remember in this case, in the autonomous case, it meant that if we had one integral curve, we could translate it horizontally and again get an integral curve. But it also means that in this, so what that, translating that to this situation, this means that if we have one integral curve for this, for this slope field, if we have an integral curve for that slope field, we can translate that integral curve vertically and again get an integral curve. That vertical translation is precisely what this plus c here is doing, because you know that you can take any function, right, and just add to translate its graph, let's say, horizontally, or vertically, you just add a constant to the form. So I'm not saying anything that you don't know. If you know y equals x squared, for example, the parabola, smiley face parabola, then you know that y equals x squared plus 1 is that smiley face parabola translated 1 unit upward. And similarly, you know that y equals x squared minus 5 is the smiley face parabola at the order translated 5 units downward, right? In other words, these numbers that are appearing here are precisely the values of this constant, this additive constant of integration. It just translates upward and downward. Okay, all I'm trying to do is make a connection for you between this concept of slope field, the structure of this first order equation, okay, and the geometry of the solutions, right? How we get some insight into certain symmetries, I'll call them, by understanding symmetries within the like in certain invariances that are happening in the slope field. Okay, this is very strange. I'm going to stop here.